Welcome back to AI.Code.Cast. Today, we're going to dive into a challenge that's all about music playlists.
Sounds fun.
Yeah, 60-minute playlists to be exact.
Yep.
So imagine you have just a whole bunch of songs, and you want to find all the pairs of songs that add up to exactly an hour.
I like it.
Yeah.
So sounds straightforward enough, right? But there's
Yeah.
this is where it gets interesting. There's a trick to solving this efficiently, especially when we start thinking about like really big music libraries.
Okay, so if I were just starting out with this, my first thought might be to just check every single pair
Yeah.
and see if they add up to 60 minutes, right? Is that
Yeah.
kind of what you're talking about when you say a brute force approach?
Exactly.
Yeah.
Yeah. It's like you have this giant key ring and you're trying every single key to find the one that unlocks the door.
Yeah.
You'll eventually find it, but it could take a really long time.
Right.
Especially if we're talking about like thousands and thousands of songs.
Okay, so what's the problem with that? Is it just that it's slow?
Yeah, it's mostly about efficiency. Like
Yep.
in coding, we talk about this as time complexity.
Right.
And brute force, in this case, would have a time complexity of big O of n squared, where n is like the number of songs.
Okay, hold on. Time complexity. Could you break that down a little bit?
Yeah.
I'm not super familiar with that.
So think of it this way. If you have 10 songs
Okay.
and you're using like a brute force approach, you're basically doing 10 times 10 comparisons.
Right.
But if you have like 1,000 songs, it jumps up to 1,000 times 1,000 comparisons.
Okay.
And the time just explodes.
Yeah, that makes sense.
Yeah.
So there must be a better way to do this without checking every single pair.
Absolutely.
Yeah.
And that's where the remainder trick comes in.
Okay.
So instead of focusing on the total duration,
Okay.
we're going to look at what's left over after we divide each song's length by 60. And we call that the remainder.
So instead of adding the songs up, we're looking at what's left over. Okay, I'm intrigued.
So here's why it works. If the remainders of two songs add up to 60, then their combined duration is definitely divisible by 60.
Can you give me an example of that?
Yeah, so imagine you have a song that's 75 seconds long.
Okay.
When you divide 75 by 60, you get a remainder of 15.
Okay.
Now, if you find another song that has a remainder of 45,
Okay.
those two songs together will perfectly fit into a 60-second slot.
That makes sense. So how do we actually use this to build out a solution?
Yeah.
To just like go through every song and calculate the remainder and then...
That's a good start.
Yeah.
But how would we keep track of all those remainders and
Right.
quickly find the ones that add up to 60? What kind of data structure comes to mind?
Yeah.
Yeah, to manage all those remainders, we can use a handy tool called a remainder counter.
A remainder counter, huh?
Yeah.
Sounds intriguing.
Yeah.
What is that exactly?
So basically, it's a way to store how many times we see each possible remainder,
Okay.
and we can use an array for this.
Okay, so if we have a song that's 75 seconds long,
Yeah.
its remainder is 15,
Yeah.
we would just store that somewhere in this
Exactly.
remainder counter.
Our array would have 60 slots from 0 to 59,
Right.
representing all the possible remainders you could have when dividing by 60.
And each slot would hold the number of songs that have that remainder, right? So we would initialize it to 0 at the start.
Yeah, it's like having 60 empty buckets lined up,
Okay.
ready to collect our songs based on their remainders.
I like that.
Yeah.
Okay.
So walk me through, what would we do when we encounter our first song with a remainder of 15?
Okay, so we go to slot number 15 in our array.
Right.
And we would increase the count from 0 to 1
Yeah.
to show that we've seen one song with that remainder.
Perfect.
Okay.
Now, let's say the next song has a remainder of 45. What would you do?
I'd go to slot 45 and increase that to 1, but 15 and 45 add up to 60.
Exactly.
So is that a pair?
Absolutely. That's the magic of the remainder trick.
Oh.
Because since their remainders sum to 60, we know that they will make a perfect 60-minute combination.
But how do we actually count that, though?
Yeah.
Without comparing every song every time?
That's the part that's a little bit tricky, right?
Yeah.
We can't just keep adding to the count every time we see a remainder.
Right.
Because that same song with the remainder of 15 might be part of other pairs later on.
Right, exactly.
Yeah, so there's a clever way to handle that.
Got it.
Instead of just increasing the count for every remainder we encounter,
Okay.
we only increase it after we've checked for a complementary pair.
Okay.
Okay, so let's say we encounter a song with a remainder of 30.
Okay.
What do we do?
First, we need to figure out what the other number is to add up to 60, right?
Exactly. So the complement of 30 would be
30.
Yes. So we would look at slot number 30 in our array.
Okay.
Now, before we increment the count in slot 30,
Okay.
we check its current value.
Okay.
This value tells us how many songs we've already encountered that have a remainder of 30 and are just waiting for their complementary pair to show up.
So if there are, say, 2 songs already in that slot,
Yeah,
that means we found 2 new pairs.
exactly.
Okay.
So we add 2 to our total pair count.
Gotcha.
And only then do we increment the count in slot 30 to include our current song.
Oh, okay.
That way we avoid any overcounting.
So we go through each song,
Yeah.
calculate the remainder,
Uh-huh.
we check for the complementary remainder,
Yep.
add that count to our pair count,
Exactly.
and then update the count for the current remainder. Nailed it.
Okay.
And think about it. We're only going through our list of songs once.
Right.
No nested loops, no comparing every song to every other song.
Okay.
That's why this is so much faster than brute force.
Yeah, yeah.
It all boils down to that remainder trick.
Right, right.
So you mentioned space complexity earlier.
Oh, yeah.
What does that refer to in this context?
Well, I'm assuming this approach uses, some memory
Yeah.
to store all this. Absolutely. It uses a little extra memory to store that remainder counter.
Right.
But in this case, since we have a fixed number of possible remainders, 60s,
Right.
the space complexity is what we call constant, or big O of 1.
So no matter how large our music library gets,
Yeah.
the size of our array stays the same.
Exactly. We only need 60 slots.
I see.
Now,
Yeah.
here's something to consider. What if we used a different data structure
Okay.
instead of an array for our remainder counter?
Interesting.
Yeah.
Is there another way we can store and look up these remainders? We were
Yeah.
just talking about the remainder counter and using an array.
Right, right.
But you hinted that there might be other ways to do this.
Yeah.
What else could we use?
Well, another popular data structure that comes to mind is a hash map.
Okay, a hash map.
Yeah.
Remind me how those work again.
Yeah, sure.
I know we've talked about it before,
Uh-huh.
but I need a little refresher.
So imagine a hash map as like a super organized storage room.
Okay.
Each item in the room has a unique label.
Okay.
We call that the key.
Right.
And each label points to a specific location where the item is stored.
Gotcha.
We call that the value.
Okay, so in this case, the key would be the remainder,
Yeah,
and the value would be the count.
exactly.
Right.
So instead of having an array with fixed slots,
Right.
we have this flexible structure where we can add these key value pairs as needed.
Okay, so if we encounter a song with a remainder of 15,
Yeah.
we just check if the hash map already has a key for 15.
Yep.
And if it does, we increase the count.
Yeah. What if it doesn't?
Then we create a new entry
Uh-huh.
with 15 as the key
Yes.
and set the count to 1.
Exactly. So with a hash map, we don't need to
Right.
pre-allocate all that space for all 60 possible remainders.
Right, okay. That makes sense.
We only create entries for the remainders we actually encounter.
So both of these approaches would let us use this remainder trick.
Right.
Are there advantages to using one over the other?
That's a great question. In this specific case, where we know we have a fixed range of remainders
Right, right.
from 0 to 59, an array is probably a bit more efficient,
Okay.
just in terms of memory usage.
Yeah, because we're just kind of setting aside that space in the beginning anyway.
Exactly.
Okay.
But if we were dealing with a problem where the range of possible remainders was much larger,
Yeah.
or maybe we didn't know the range beforehand,
Right.
a hash map would give us more flexibility.
It's like those expandable containers,
That's a great way to put
They
it.
just get bigger.
Yeah.
So it really depends on the constraints of the problem and what we
Yes,
care about,
exactly.
whether it's memory or flexibility.
Yep.
So in our case,
Yeah.
either approach works.
Exactly.
But it's cool to see how different data structures can be used to solve the same problem.
Absolutely.
This has been a really fun deep dive. We explored the brute force approach,
Yeah.
learned about the remainder trick, and even talked about how arrays and hash maps can help us implement efficient solutions.
I hope this has inspired you to think about remainders
Yeah.
and how they can help you optimize your own code.
Absolutely. Thanks for joining us on AI.Code.Cast. Until next time, keep coding and keep exploring.